Hi everybody, welcome to IZ8 DWF channel. This is the third pole position arcade board set repair. If you haven't watched the previous videos, links are down in the description. The first one is especially important since I'll give for granted many information already shown on it. This board set was the one in worst visual conditions of all four received, for a lot of different reasons as we're going to see. For example, one custom IC, a NAMCO 521, is completely missing, so I will try to make a replacement for it. Also, a number of other ICs were already socketed during a previous repair attempt. As we have seen, the NAMCO 52 IC is completely missing. The board came with a label reporting the 5258 number. However, only the first two digits matter for a NAMCO custom IC, as the last two indicates probably a date code or something similar. If the board set can be fully repaired, I'll try to make a replacement for this custom IC. It is basically used as a digital to analog converter to play the voice effects. Then, also on this board, there were two Z80 CPUs in place of the Z8002 16 bits ones, so I've installed these UB8002 replacements. When ICs have been replaced in a previous repair attempt, it is always a good idea to look up the substituted parts on the schematic. Notice this 74F163 in position 7B. It is a clock divider and it is indicated as 74S163. Now, the 74S family is a much faster version than the 74LS, but luckily the 74F ICs have almost the same propagation delay of the 74S ones, so the IC we found is a good replacement for the original one. However, in position 7N of the CPU board we have a socketed 7404. But on the schematic, this IC is indicated as S04, so again a fast TTL family. And a plain old 7404 is not for sure as fast as a 74S1, so I placed the proper IC in the socket. Then we have these other two socketed ICs in position 6K and 6J, both are 74157 ICs. According to the schematic, they should be 74LS157, but the old 74 family and the 74LS1 have very similar propagation delays, so I won't substitute them at this stage. Another very interesting thing is that also the two RAM ICs shown in this part of the schematic have been socketed, so I guess this board showed some stubborn audio problem. This CPU board also is the one with the worst battery leakage signs. Notice that the solder joints show a much darker color than what normally should be. The damage is evident also on the bottom side. I've tried to apply fresh solder to the worst joints. And here the copper trace that connected CR5 to the plus terminal of the battery is completely gone. So I've added a piece of wire to restore the missing connection, in case someone wants to connect a backup battery again. Of course, it will be better to relocate the battery into an external holder and connect only the wires to the PCB. Now, many NAMCO custom ICs have been labeled because some of their pins have been already soldered. However, I'm going to inspect all of them and see what else needs to be done. On this I see a pin detached very close to the plastic case, but I think there is enough metal surface to reattach a new pin, so I've carefully removed all the oxide layer with a small file. Then I've reinserted the IC into its socket, and after that inserted the new pin in the socket and aligned it to make a good contact with the metal fragment left on the IC side. At this point the pin can be soldered quickly. And last, a drop of epoxy glue can be applied around the soldered pin to enhance its mechanical strength. Even this other IC does not look too good, but with enough patience all pins could be reattached. In this case the metal fragments were large enough, so all the work could be done with the help of a third hand. However, not every IC could be saved. One 03 custom IC had all pins heavily corroded, and it kept on losing them as soon as I was trying to clean enough fragment still attached to the case. Eventually, not enough fragments were left on its body to attempt a restoration. At this point, I really need to find a working replacement for this particular custom IC. On the pole position video PCB, there are only two 03 custom ICs. It seems that at least a couple of other persons already reverse engineered all NAMCO custom ICs, but none of them even answered my messages. So it seems I have to understand how these things work. What we can observe here is that they get a clock signal, which is a 6 MHz one in this case, then they have 4 bits data inputs from a couple of TTL proms, and notice that the second one gets its inputs from the first 03 output pins. So in practice, whatever they are, their function is applied twice to the same data. Then we have some control inputs that modify the way they operate on the data. This suggests that probably the same function is applied on all the data bits. Now, if I had a logic analyzer, this reverse engineer job would be probably quickly done, but the proper old analyzers are quite expensive things. The troubleshooting guide suggests that when failing, they will affect both the background and the raceway, but at the moment this information doesn't seem to help much. So I took a good 03 IC and started playing with it on a breadboard. I can toggle inputs by moving wires between 5 volts and ground, and use a function generator to provide a square wave clock. The outputs can be monitored with the oscilloscope. Luckily, the internal memory elements are just static flip-flops, so the clock frequency can be as slow as we want. The clock period is about 2 seconds now. The bottom trace shows the clock and the upper one is one output bit. And in this case, at the 4th clock rising edge, the output toggles. So at a first glance, these IC are 6-bit wide, first in, first out memory blocks with a variable depth. Only 4 bits are used in the pole position video PCB, but I still haven't figured out how the variable shift depth is controlled by the 3 mode inputs. I clearly need some sort of automatic logic signal generator and analyzer. The fastest option for me is to use the Commodore PET user port. In particular, these pins can be configured individually as input or outputs, so I can write small programs that change the input bits and show the output bits at various clock cycles. Of course, any other old Commodore computer I have at home has a very similar interface, but the PET happens to be the more convenient one to use at the moment. So here we are. I've drawn a more or less final logic schematic for this IC. This is one of a few programs I wrote. Well, okay, I needed some more work to really have a schematic that does what I'm observing with the help of the various programs. But after one full afternoon, here we are. First of all, the entire IC can be modeled with 4 edge triggered flip-flops that are more or less cascaded and all get the same clock signal. Of course, I'm showing only one data bit here, but all the 6-bit data paths are identical. Then the control pin number 8 just selects what we get at the output pin. If it's 0, the output is connected to the input of the last flip-flop. If it's 1, the output pin is connected to the output of the last flip-flop. And last, the 2 other control pins, 10 and 11, select what is connected to the input of the last flip-flop. And that can be the input pins directly or any of the other flip-flop outputs. Notice that when all control inputs are at logic 0, the data inputs are just connected to the output pins directly and bypassing any clock delay. So, with this information, I can finally make an adapter circuit. I've chosen to use a single CPLD to substitute both the 03 custom ICs on the video PCB, since they are very close to each other. Of course, I will implement only the 4 data bits that are actually connected. The CPLD is placed between the two pin strips that go into the sockets where the original ICs used to be. Then I converted the reverse engineered schematic into a CUPL source file to be compiled for an Atmel ATF1504 CPLD, that is a chip still in production and working at 5V supply, so it doesn't need any voltage regulator or level adapter to be interfaced to the old TTL logic. In reality, my original idea was to use a 32 microcell ATF1502. But I couldn't make my design fit on it. As you can see, it uses 40 cells even if the active flip-flops needed are only 32. Price difference between the two is really small anyway. At this point, I only needed to wait for the PCB to arrive, so I could populate one and install it on a non-working pole position board set for the final test. And yes, it looks good to me. I think I can proceed with the repair of the other board set now. Of course, I've published this replacement in my GitHub space too, so it can be reproduced if needed by someone else. A link to it is down in this video description. So let's power on. It seems just stuck. As we have seen in the first video of this series, the boot process is started by the Z80 CPU, so I'm going to check its clock pin and the reset pin first. The clock signal looks okay. And the reset pin is permanently high. But the watchdog is pulsing. And again, as I've explained in the first video, the reset circuit contains a design error, so it doesn't work correctly when the watchdog is pulsing, and I'm going to substitute the right IC later. In fact, the reset line is kind of pulsing, but never reaching 0 volts. However, the reset circuit is not for sure causing the stuck screen, so I'm going to add this NOP generator socket under the Z80 to check the address decoder PLD. Pins 12 to 19 must all toggle with a NOP generator. But 17 is stuck high. And 18 too. Yes, this PLD is faulty. So I need to remove the old PLD, but the battery leakage turned the old tin into a very stubborn material. Eventually, by adding a lot of fresh solder, the IC could be removed. No traces or pads seem to be damaged on the top side. And after cleaning all the flux residues with alcohol, even the bottom side doesn't look too bad. The CMOS inverter in the problematic reset circuit has been substituted with a 74HC14. And of course, in place of the old PLD, I've installed a socket and programmed a 16V8 replacement as already shown in both the previous pole position repairs. Well, now we have this RAM7 error. According to the service manual, RAM7 indicates a problem with the IC in position 7K. At the beginning, however, we have seen that both 7J and 7K static RAMs have been socketed, and of course, one of the first things I've done was checking the socketed RAMs and ROMs of all the pole position PCBs that I have received. So let's see what we find. And this pin is floating. The same pin on 7J is pulsing. Well, a very good reason for a floating pin is that whoever socketed this IC forgot to solder it. I reflowed all the pins, so no more missing solder. And then I took some time to inspect all other socketed ICs, and sure enough, here is another forgotten pin. And here is another unsoldered one. Luckily, they gave up on this repair. So, let's try again. And yeah, it's starting now. But, it doesn't sound good. And indeed, almost all sound effects are not working. The explosion sound is okay. This other one sounds good too. But here all the others sounds like high-pitched noise. Also the car engine sound seems fine. The engine sound is generated by a dedicated circuit, so we can exclude this one. The speech custom IC is entirely missing, so sounds number 19 and 20 are still silent, but the skid sound is probably made by the upper circuit in this image. Now almost all sounds are going through a 4051 CMOS analog multiplexer and some variable gain blocks made with 4066 CMOS analog switches. Then probably these circuits are working well. So all the faulty sounds are made with this 4 bits weighted resistor digital to analog converter. This means the problem must be in one or more of these ICs, so I'm going to check with the oscilloscope if I find some bad signals on their pins. Sounds 10 or 11 play in a continuous loop, so that's perfect for keeping the circuit alive during troubleshooting. Now I'm examining IC at 10E, and pin 1 doesn't look good already. This input looks fine. This is another input. And yes, another output is dead. Another bad output. Yes, this IC is definitely bad. In position 10E we have a 74 LS283 4 bits adder and all its outputs were bad. So I pulled the old IC, installed a socket and a replacement LS283. And let's see what happens. As you can hear, sound effects are correct now. But of course 19 and 20 are still silent. Now this board set is back to full functionality except for the missing 52 custom IC. So let's see what we can do about it. First of all, let's understand what it does. It's basically a 4 bits microcontroller with internal program ROM, RAM, timer and input-output ports. A 4-bit word is read on these input pins when the IO2 line goes low. This is how the main sound CPU starts a speech playback. At this point, the 52 custom reads a segment of the external ROM space that just contains digital audio samples, and plays back each sample at a fixed rate using its internal timer. The samples are 4 bits wide and are converted to an analog signal by 4 external resistors. But, of course, figuring out all the finer details from scratch would be quite a time-consuming job. Luckily, someone else already published a very good explanation of the internal details of this NAMCO custom IC. On this web page, linked down in the description, there is also a pseudocode description of the internal microcontroller firmware. It cannot get better than this. Of course, this custom IC has also been completely emulated in MIME, so another very good source of information about it is in the main source code. So I can learn, for example, that you can behave differently and use an external playback clock too. Apparently, this is used, for example, in the Bosconian arcade game. To make a functional replacement, I've decided to use an ATmega 8515 8 bits microcontroller, just because it has the right amount of input-output pins, small enough footprint, and I'm quite familiar with its AVR assembly language, since I've been using similar CPUs for more than 20 years. I started assigning the various functions to the input-output pins of the chosen microcontroller. Of course, some pins have special functions, so I'm kind of forced to use a few of them. For example, I want to generate a hardware interrupt whenever the main CPU has an ID to communicate, and I need also to reserve a timer input pin for the playback clock in case it's needed. Other than that, I want the interrupt service routines to be as small as possible. So, for example, when the main CPU writes an ID, all interface pins are read with a single input operation, and the service routine is very small. Half of the instructions are needed to save the internal status register and to return from the interrupt call. The timer interrupt that outputs the actual 4-bit sample to the external port is a bit longer, but that's because half of the 8 bits of port C are used for addressing the external ROM, and the other half are used as the digital sample outputs. Anyway, the playback rate is very slow, so this will work. So, once all pins are assigned, a quick and dirty PCB can be designed with KiCad. After a few weeks, I received the real PCBs. Pins can be soldered by putting them into a socket that keeps them aligned nicely. I didn't even provide a programming connector, so I just wired the programming pins to my homemade AVR programmer. And it worked well. The program has been written to the MCU program flash memory. At this point, the 52 custom replacement can be inserted into the socket in the Pole Position CPU PCB. So, let's see what happens. Of course, all the other sounds aren't affected. Yes. It worked well, it seems. Of course, I published all files and information for this project in my GitHub space. So this boardset is now completely working. I hope this repair was interesting and that you learned something. If you have any question, please use the comment section below. Have a nice time and thank you for watching.